All right, let's look at another example. This one involves Newton's law of cooling. If D naught is the initial temperature difference between an object and its surroundings, and if its surroundings have temperature T sub S, that's the temperature of the surroundings, then the temperature of the object at time t is modeled by the function capital T of lowercase t equals capital T of S plus D naught times e to the negative kt, where k is a positive constant that depends on the type of object. Let's take a look at an example that uses Newton's law of cooling so we can see how it works. A cup of coffee has temperature 200 degrees Fahrenheit and is placed in a room that is 70 degrees. After 10 minutes, the temperature of the coffee is 150 degrees. Find a function that models the temperature of the coffee at time t. Find the temperature of the coffee after 15 minutes, and when will the coffee have cooled to 100 degrees? So we're going to use Newton's law of cooling, which I'm going to rewrite down below here. Capital T of T equals capital T sub S plus D naught times e to the negative kt. And I want to substitute in the values that we know here. So we know that the original temperature of the surroundings is 70 degrees Fahrenheit, so this will be 70, plus the initial difference in temperature. Well, the coffee was 200 degrees and the room was 70 degrees. The difference there is 130 degrees times e to the negative kt. Now, we're not told what this constant is. It's different for every substance. It would be different for coffee or oil, or if we had a car that was very warm and it was outside during winter. Every object, depending on the material and the size and all sorts of other things, has its own constant. And we don't know the constant, but we can figure out the constant based on the fact that after 10 minutes, the temperature of the coffee is 150 degrees. So we know that the temperature is 150 degrees when t, lowercase t, is 10 minutes. If we substitute both of those in, the only variable left is k, that constant, and we should be able to solve for it. And once we do, we'll know the whole equation for our function. So let's solve for k. We're going to subtract 70 from both sides. That gives us 80 on the left equals 130 e to the negative k times 10. And we can get rid of this 130 by dividing both sides by 130. If we do that, the left-hand side reduces to 8/13. So we have 8/13 equals e to the negative 10k. It's a little bit nicer than writing negative k times 10. Now, if we rewrite this in logarithmic form, this gives us the natural log, because it's base e, of 8/13 equals negative 10k. And to get k alone, we need to divide both sides by negative 10. So we have the natural log of 8/13 all over negative 10. This is the exact value of k, but what we're going to do is we're going to get an approximation, because that's going to be easier to put into our equation. And when we plug this into a calculator, we end up with a value of k that's approximately equal to 0.0486. I'm going to round to the 4th decimal place. I think that that's good. So our function, we didn't know what the value of k was, but now we do. So we can plug that in, And our function that models this temperature is T of little t equals 70 plus 130 times e to the negative 0.0486 t. So this is our function. Oftentimes, we might find ourselves in a situation where we've got a formula that has a constant, and we might not be told that constant directly, but we might be given enough information to figure out what that constant is. And that's what happened in this situation. So we've found the function, that's the first part. Now we want to find the temperature of the coffee after 15 minutes. So we just need to evaluate this function when little t equals 15. When we do this, we get t of 15 equals 70 plus 130e to the negative 0.0486 times 15. And we can just plug this into a calculator to get an approximation. And we end up with approximately 132.7 degrees Fahrenheit. So after 15 minutes, the coffee has cooled to 132.7 degrees Fahrenheit. And this should make sense. It started off at 200 degrees. After 10 minutes, it got to 150. And the surroundings are still cooler than the coffee. So the coffee should still be cooling down. And after another 5 minutes, it ends up being about 133 degrees. So this makes sense. Now the last question, when will the coffee have cooled to 100 degrees Fahrenheit? Maybe that's the temperature that the person likes their coffee the most, and they want to know how long they'll have to wait for that. In this case, we know that the value of capital T needs to be 100. So we substitute in 100 for capital T, and we need to solve this equation now for lowercase t. So we've got this function, and we've plugged in 100 for the function value for the temperature, and now we need to solve for lowercase t. So when we do this, we subtract 70 from both sides. That gives us 30 equals 130e to the negative 0.0486 t. And then we divide both sides by 130 to get rid of that coefficient. When we do that, the left-hand side reduces to 3/13, and that equals e to the negative 0.0486 t. We can rewrite this in logarithmic form. That gives us the natural log of 3/13 equals negative 0.0486 t. And to get t alone, we divide both sides by negative 0.0486, and this gives us ln of 3/13 divided by negative 0.0486 equals t. And when we approximate this value with our calculators, we get approximately 30.17, close enough to 30. So it will take approximately 30 minutes for the coffee to cool to 100 degrees Fahrenheit. So we've answered all of the questions, but I do want to take a quick look at the graph of this function so we can talk about it. So here we have the graph of the function. This is temperature as a function of time. And it starts off at 200 degrees. And we notice that the temperature starts decreasing. And it continues to decrease, but it's decreasing less and less. And it looks like it's asymptotically approaching 70. And the reason for that is because it's placed in a room that's 70 degrees. The coffee is never going to get colder than the room that it's in. It's always going to get closer and closer to that temperature, and that it's going to start cooling off the most quickly in the beginning, and then once the temperature difference is less, it's actually going to be cooling down slower and slower and slower. So in general, Newton's law of cooling means that whatever the temperature is of our object, it's going to start cooling down fairly quickly while the temperature differential is pretty big, and then it's going to slow down once that temperature differential is smaller. And if we're in a situation where we have a coffee cup where the coffee's colder than the surrounding temperature is, we're going to see that it's approaching from below, and so it's going to be warming up more and more, getting closer and closer to that ambient temperature. I think that this is a very good example of an interesting law of nature, of physics, because here we know that every object has a different value of k, a different constant. And it might not be clear how to calculate that constant for a particular object, what it depends on. But if we have just two temperature readings, the initial reading and then the reading several minutes later, that's enough information for us to solve for that constant and figure it out. And once we've done that, we know everything we need to know about that temperature function and how the temperature is going to change over time.